This is the fourth and final section of the modelling with differential equations chapter, and here we're going to be looking at coupled first order simultaneous differential equations. What a mouthful. Anyway, what this is about is where we have two differential equations which interact with each other. So a change in one impacts a change in the other. So we've got two first order differential equations where they use different variables, and the way that we deal with them is we're going to eliminate one of the variables like x or y, so that we end up with a single equation, and that's the method we're going to use. Okay, at the start of year 2010, a survey began on the number of bears and fish on a remote island in northern Canada. After 2 years, the number of bears x and the number of fish y on the island are modelled by differential equations. So the number of bears and the number of fish, the change in the rate of their population, they're interdependent. So as the rate of bears goes up, maybe the rate of fish goes down. As the rate of fish goes up, the rate of bears goes up. And we've got two differential equations, one to model the number of bears, which is x, and one to model the number of fish, which is y. And you can see that these sort are interconnected with one another because this equation contains x and y. So this is telling us, well, the change in the number of bears over time is actually linked to the number of bears and the number of fish. And the second equation, where we've got this, it's telling us that the rate of change of the number of fish over time is linked to the number of bears and the number of fish. Yeah, so they're both linked together, they're coupled together. So that's why they're called coupled equations. Coupled just means they're interlinked, they affect each other. Okay, right, part A. We need to show that the second order differential equation formed by these two first order differential equations is this. Now you'll notice that we're trying to get an equation here that doesn't have any y's in it, so we need to eliminate y. So that's the process we're going to take. Now it could be that you have a second order differential equation where it's d squared y over dt squared and so on, in which case you would eliminate x. So we need to make y the subject of an equation and then substitute it into the other equation. Now we'll start by taking equation number 1 here and making y the subject. So let's just write that down. So dx dt equals 0.3x plus 0.1y. So I could times both sides by 10, move the y over. So I'll have y equals, and then I will have 10 dx dt minus 3x. So that will allow me to eliminate y in the second equation, but I also need to eliminate dy dt. Now that's why I actually made y the subject of this first equation and not y the subject of this second equation, because I want to get rid of the y and the dy dt. Yeah, I could do it the other way around and make y the subject of this and use it to eliminate y from here, but then it just becomes a bit tricky in terms of getting rid of the dy dt from the equation that we've already got dx dt in. Yeah, so yeah, it's better to do it that way round and see, right, look at the equation that has the y's in, say, right, I want to get rid of that, so I'll rearrange the first equation. I want to get rid of this, so again, and then we'll differentiate that first equation once it's been differentiated, right, or eliminated. Right, so we're now going to differentiate this with respect to t, so I'll have dy dt. Now when I differentiate this term with respect to t, I'm going to write this. I'm differentiating this term here with respect to t. And then the minus 3x, so the x, when I differentiate it with respect to t, this is like the implicit differentiation. So if I were to differentiate 3x, it would become 3, but I need to write that I've just differentiated an x term as if it were a t. So this is the implicit differentiation, which you have done in Pure 2, implicit differentiation. So let's just tie that up. So that will give me, dy dt equals, now this will become 10 d squared x dt squared. So you can probably see why we write d squared, because it's like d times t, so d squared x, and dt times itself is like dt all squared. Basically just write dt squared, and then minus 3 dx dt. So now we've got an expression here that we can use to get rid of dy dt from the second equation, and we've got another expression here which we use to get rid of y from the second equation. So that's going to be the next step, is to make that substitution. So we'll replace dy dt with this. So we now, let's write it down, sub into equation 2. So yeah, dy dt, which is 10 d squared x over dt squared minus 3 dx dt. That's dy dt equals negative 0.1x plus 0.5y, and y is 10 dx dt minus 3x. That can be tidied up. So I'll have 10 d squared x dt squared. Now I've got minus 3 dx dt. From this side I'm going to have 5 dx dt. So I'm going to have 3 of them, and I want to take off 5 of them, so I will have negative 8 dx dt. Then in terms of my x, I've got negative 0.1, which will be plus 0.1 on the other side, and then I've basically got 1.5, negative 1.5x, which will become plus 1.5. So I'm going to have 1.5 plus the 0.1, so I'll end up with 1.6. So plus 1.6x equals 0, and I think you can see if we then divide everything by 10, we'll get the form as required. Okay, so we'll just write down what that will be. So I'll just put dividing by 10 here. So d squared x dt squared minus 0.x or 0.8 dx dt plus 0.16x equals 0 as required. So that's part A. Now part B, it's asking us to find a general solution for the number of bears on the island at time t. So since this is equal to 0, then we don't need like the complementary function or anything like that, just the auxiliary equation. So the auxiliary equation is going to be m squared minus 0.8m plus 0.16 equals 0. So I think I will probably use my calculator to help me solve this. When I do use my calculator, I get a solution of m equals 0.4. You can check that on your calculator. You might be able to sort of work it out yourself. We'll get this m minus 0.4, m minus 0.4 is basically what we get when it's factorised, so it does factorise. So that's going to be our value of alpha in our general solution. So when we have a single root, remember the solution is of this form, so x equals, and in brackets, a plus bt times by e to the power of alpha 0.4t. Part C is find a general equation for the number of fish on the island. So we now want an equation, a general solution, which is y equals, now we don't need to go back to scratch and rearrange this and make x the subject and substitute. We can just use this. Y equals 10 times dx dt, so 10 times this differentiated minus 3x. So that's going to be a much quicker way to do it. So we're going to need dx dt. So dx dt we can get by differentiating this, and again I'll use the product rule. I'll call this bit u and this bit here v. I could expand the brackets, that's another way of doing it. So I will have a plus bt times by v dash, which is going to be 0.4 e to the 0.4t plus, and then I differentiate the first bracket. Don't want to make the same mistake as I made in a previous example. That will become b, not t, times by e to the 0.4t. Okay, so that's dx dt. Now I can just substitute this 10 times this, yeah, minus 3 times this to get y. So I'll probably want to just tidy this up a bit. One of my favourite phrases is tidy up. So I will have 0.4. Actually, there's probably not much point now. I'll write it as a plus bt to the e 0.4t plus b e to the 0.4t. So y is going to equal basically 10 of these, yeah, 10 of those, which would be 4 a plus bt to the power e to the 0.4t plus 10b e to the 0.4t, and then take away 3 of these. So I'll do minus 3 a plus bt e to the 0.4t. Now if I simplify that, I will have y equals, now I've got 4 lots of a e to the 0.4t, take away 3 lots of a e to the 0.4t, will just leave me with 1 lot of a e to the 0.4t. With the b terms, I've got 4 bt's here, take away 3 bt's here, so that just leaves me with 1 bt e to the 0.4t, and my b terms, well, I've got 10 of them here, so they just get added on the end, plus 10 e to the 0.4t. So maybe it's a good point here to just highlight some answers. So there's my part C answer. like this. My part B answer, now where was that? That was, alright, that's over here. Let's just highlight that. That was my part B answer there. Let's take away the U and the V so it doesn't cause confusion now. Part A was just the proof, wasn't it? Right, let's move on to the next part of the question, part D. At the start of 2010, there were 5 bears and 20 fish on one island. Use this information to find the number of bears predicted to be in the island in 2020. So let's make a little bit of space at the top so I can finish off D and then E. Right, so part C, we'll do that at the top here. We've got a bit more space. Oh, sorry, no, it's a part D. Since we're trying to find a number of bears, we want our equation that gives us the number of bears, not the number of fish. And that is this one here. That's our general solution for the number of bears. X equals A plus BT E to the 0.4t. And we're told at the start of 2010 there were 5 bears and 20 fish on the island. We're going to use that information to find the value of our constant. So starting with t equals 0 and number of bears was 5, so x equals 5. So that will give us 5 equals A plus B times 0, so B's gone. E to the 0.4 times by 0. So that will give me A equals 5. Let's just box that. A equals 5. Okay, so to find Y, we're going to use the other equation for the number of fish. Now the values of these arbitrary constants here are the same in both equations because they're coupled, they're linked together. And I did notice that I forgot to put B here, so I've just slotted that in. Hopefully nobody noticed. So yeah, we're going to put t equals 0 and y equals 20 because there are 20 fish at the start into this equation here. Now I've got the value of A, so that can go in as well. So 20 for y equals A times 0.4 to the power 0. So basically I'm just end up with A there, which is 5. Won't write all the working out. Then this second term disappears because t is 0. Then the third term just becomes 10b. So plus 10b. So for that we can work out b. So I'll have 10b equals 15. So then b equals 1.5. So we have the values of A and B. And then we're going to get our particular solution. And that equation we can now use to answer the question. So it's going to be x equals 5 plus 1.5t e to the 0.4t. And the question is asking, use this information to find the number of bears to be predicted on the island in 2020. So that's going to be when t is 10. Yeah, because t is the number of years. Yeah, so we just substitute t as 10. Not sure why I've written t as 0, because I'm probably so used to writing that. So the number of bears will equal 5 plus 1.5 times by 10 times by e to the 0.4 times by 10. And what does that give me for x? So I get 1091.963. So obviously we want a realistic answer. So 1092 or even 1091, you'd probably be allowed. Yeah, it may not have got to 1092 bears. Okay, so there's the number of bears after 10 years. Part E, comment on the suitability of this model. Now let's think about it. After 10 years, we've now got over 1,000 bears in northern Canada. That's excessive. Like, are they going to keep growing without ever stopping? No, that's not going to happen. And if you were to try a larger value of 10, of T, let's say 100, let's try that. So in 100 years, I would get 3.6487 times 10 to the power of 19 bears. That's an awful lot of bears. So, not really realistic for large values of T. So comment on the suitability of this model. So the model is not realistic as T gets larger. Yeah, for a certain number of years it might work, but after that, not realistic. Okay, so here again we have two coupled equations, 2 barrels containing contaminated water at time t seconds. The amount of contaminant in barrel A is X milliliters, and the amount of contaminant in barrel B is Y milliliters. Additional contaminated water flows into barrel A at a rate of 5 milliliters per second. Contaminated water flows from barrel A to barrel B and from barrel B back to barrel A through 2 connecting hoses and drains out barrel A to leave the system completely. Okay, and what we need to do is we need to derive this second order differential equation, and notice that it's in terms of y. So in this question, unlike the other one, we need to eliminate x. In the other one that we did, we eliminated y. So this time we need to use the second equation here and make x the subject. So let's write the equation down. So dy dt equals 3 over 70x minus 9 over 4y. 4 over 9 y. So the first step would be really multiplied by 70. So we've got 70 dy dt equals 3x minus 280 over 9y. So yeah, we can say that x equals, when we rearrange it, that means dividing both sides by 3 as well. So it will be 70 over 3 dy dt plus 280 over 27y. We'll now differentiate this to find dx dt, because we need to eliminate dx dt as well. So remember, we've got this 70 over 3 dy dt, and what am I doing? I'm differentiating this with respect to t. Yeah, differentiate everything with respect to t, and then using the implicit differentiation here, I've got a y term, which if I differentiate it implicitly, that will be just 280 over 27, and I need to write down that I've differentiated a y term as if it were a t term, so that's dy dt. So that will give us dx dt is equal to 70 over 3 d squared y over dt squared plus 280 over 27 dy dt. So now I can eliminate my x and my dx dt using these. There's my x, here's my dx dt, so the rest is just algebraic really. So that will give me, if I'm subbing that into equation 1, sub into 1, then I will get dx dt, which is this, 70 over 3 d squared y over dt squared plus 280 over 27 dy dt. That's my dx dt, and it equals 5 plus 4 over 9y minus 1/7 of x, and that's going to be 70 over 3 dy dt plus 280 over 27 y. So we just tidy this up, and I'm going to multiply everything by 27 to get rid of these nasty denominators. So 70 over 3 times by 27 is going to give me 630. So 630 d squared y over dt squared plus 280 over 27 times by 27 is just going to be 280. So 280 dy dt. Now I'm going to bring everything over to one side as well. So the 5 I'm going to, well, I'll leave the 5 there on that side. I'll bring the 4 over 9 over. So 4 over 9 times by 27 is going to be 12. So I'll have minus 12y. Then I need to sort of deal with these here and times them by 27. So I'm basically going to have 70 over 21 here, dy dt. So 70 over 21 times that by 27, I get 189 over 2. So take that over to the other side. I will add on, sorry, I typed in the wrong number. Actually, these multiply together. 70 over 21 gives me 90. So I want to add, when I take it to the other side, add a 90 dy dt. Then lastly deal with this. So I'll have a 7th times by 280. Let's type that in. Over 27, which I'm timesing by 27. So I basically just times it by 280. So it gives me 40y, negative 40y, which I'll take to the other side, which will give me plus 40y. I think that's all the terms dealt with, equals the 5 times by 27, which is 135. Now let's guess what we're going to do. Tidy this up. So I have 630 d squared y over dt squared. 630 dy squared. Let's start again. 630 d squared y over dt squared. Right, what else happens? Well, we've got 280 of these dy dt's plus another 90 of these. That's going to give me 370 dy dt. Then I've got negative 12 of these, add 40. That's going to be plus 28y. Plus 28y equals 135 as required. So there we go. That example is now done. I'll just highlight it there, but that basically it's just a proof, so there's not really much point in highlighting that, wasting ink, but there we go. Right, we should now be able to do exercise 8D on pages 188 to 190, and this is where we've got these coupled first order linear differential equations, and the way that we deal with them is by eliminating one of the dependent variables to form a second order differential equation. And coupled, the word coupled here just means linked. So we have these two differential equations which are linked to each other. A change in one is causing a change in the other. And as it says here, eliminate one of the variables, normally x or y, and then you get this second order differential equation, which we solve using the usual methods.